So my name is Doug Fairbairn. I'm here to demonstrate ICARUS, which is a program for laying out the mass levels of an integrated circuit. ICARUS stands for Integrated Circuit Artwork Utility System. And it was created in the summers of 1976 and 1977 by myself and a Caltech graduate student at the time named Jim Rowson. ICARUS had its beginnings in the spring of 1976 when Carver Mead, professor at Caltech, came up to Xerox PARC to teach a 3-day version of the course that he taught at Caltech on VLSI design. And his mission at the time was to find ways to simplify the problem of designing integrated circuits, because he saw that they were increasing very rapidly in terms of their complexity, and we needed better tools, better methodologies with which to design these complex circuits. And so he came to Xerox PARC, where there were a lot of designers working in TTL, with the goal of perhaps teaching some of them how to take their ideas and designs and reduce them to custom ICs as opposed to TTL logic, and form a collaboration between Caltech and Xerox PARC in his endeavor to improve the design process for these very complex integrated circuits. So he came and taught a 3-day version of the course, and I believe it was April of 1976. And there were several of us who thought this was an exciting new direction and chose to form a group under the direction of Lynn Conway that was called the VLSI Systems Group to work with Carver and the people at Caltech to develop better tools, methodologies for designing chips. Carver and Lynn Conway worked together in a collaboration over the next couple of years to write the book Introduction to VLSI Systems, which became a very famous book used throughout many universities around the world to teach college-level students the art of integrated circuit design, shall we say. And in parallel with that, Carver suggested that we hire this wonderful graduate student who he had at Caltech named Jim Rowson to come and join us during the summer of that same year, 76, to write a program for the Alto. The Alto by that time had become the ubiquitous tool on which everything was done at Xerox PARC, much the same way that a personal computer or your phone is today. If it can't be done on a personal computer or on a phone, then it probably isn't going to get done. And in that same light, all the engineers and pretty much everybody at PARC, or at least in the computer science and system science lab, had an Alto. And so if we were going to be designing integrated circuits, then it was clear that there needed to be a program on the Alto that would enable that process. So Jim and I set out to design develop this program, and he focused mainly on the internal algorithms. I focused mainly on the user interface, and together we created a tool that by the end of the summer was usable for designing chips. A year later, in the summer of '77, he returned, and we made further enhancements to the product. And with the exception of perhaps minor enhancements after that, I think the work that was done in those 2 summers is in fact what's reflected in the demonstration that we'll see today. And the program was not just a toy, it was actually used for the design of a number of chips, actually dozens of different chips, first to prove out the methodology and then to do actual work. I think a couple of the better known ones were one done by Dick Lyon, which was the first IC used in an optical mouse, and Jim Clark, who was at the time a visiting professor at Stanford, used the system in the evenings in the office next to mine to design a chip called the geometry engine, which became sort of the test case for his ideas about how to do low-cost graphic systems, and formed the launching pad, if you will, for his company Silicon Graphics. So in terms of educating a large number of people, proving out the viability of the design approach that we had formulated and the usability of the product, ICARUS was a significant success. So we have, 40 years later approximately, resurrected the Alto and the ICARUS program, and I'll be demonstrating that in this session today. So, as we turn to the screen, we see two main windows, the upper window and the lower window. And these are two views of the integrated circuit because an integrated circuit is, on the one hand, very complex and very detailed, but on the other hand, very large and unwieldy. And so you need two views, and we typically use the upper window for sort of the overall view of the chip and the lower window for doing the detailed design at any given point. This small rectangle in the middle of the upper window outlines the portion of the chip that is actually shown in the lower window. You can in fact use the windows interchangeably, and you can actually draw lines or other structures between the windows. For example, you could start a line that you wanted to cross the chip at the upper window and then complete it by clicking in the bottom window. To the left of the upper window are a set of basic commands, including things like quit and restarting the system and retrieving a drawing that you've already done or saving the drawing that you're already doing, redrawing the screen if things get confused. You can turn, there are grid marks that we call ticks. They're probably not visible on the video, but are useful in terms of making sure that you align various structures. You can turn those on and off. You can, of course, print the output. You can create symbols. Symbols are a very important part of ICARUS that allows you to form a hierarchical structure within your design. It's just not practical to design everything at one level, and so it's very useful to design cells or symbols that allows you to create a hierarchy of complexity. You can then also mirror and rotate the symbols. You can input text. It's often helpful to identify the purpose of certain signal lines or power lines. The text has no meaning in terms of the final function of the chip, but it is useful to annotate the design much like you would annotate the lines of code in a program. So that's the major points of this menu here. Between the two screens is another set of menus. I'm going to focus first on these squares of different, what we call stipple patterns. Unfortunately, at the time, we didn't have a color display, which would be very useful to designing the multiple layers of an integrated circuit. So we had to come up with what we call stipple patterns, or patterns of dots that could be overlaid on one another. And hopefully, if you have 2 or 3 or 4 of them overlaid, you could actually tell whether they were all there or not. Sometimes that was confusing, so you could use a command up here to appear or disappear a particular layer so that you could make sure that other layers were present below it. So there were, in an integrated circuit, there are many levels in the process of building up a circuit. And you typically start with bare silicon. You might then put a diffusion layer, and on top of that you would put a polysilicon layer, and between those you might need a connection, so we have I have contacts. Then there's a metal layer that goes over the top of all that, and a couple of other layers that are used in special circumstances. So to demonstrate ICARUS, I'm going to draw just the simplest of structures, that is a transistor with or a couple of transistors, and then I'm going to show how that can be made into a cell or a symbol, and then replicate it over the screen. And from that process is how you go about building up an integrated circuit. For a very long time, integrated circuits were designed completely by hand, even by hand drawing on Mylar. So even though this represents doing design at a very low level, the fact that it's done on an interactive screen was a significant advance for the time in which it was done. So I'm going to begin by drawing first on the metal layer. So you select the layer that you want to draw on, and then you point and click at the two endpoints that you want to draw. You then go down here, you draw another line. So the metal line is used, for example, to conduct power and ground to all of the circuit, and so is often a common starting point or reference point for the design of the rest of the chip. I'm going to then move to the diffusion layer and create a connection between this metal line, which would be power, for example, and this point down here. And by drawing them overlapping, I haven't yet connected them. So in order to connect them, I first have to put additional material down, and then I use a cutout or a contact to actually connect the two together. So now that's you've connected a diffusion line to a power and a ground, and now I'm going to actually create a transistor. The transistor is created by taking a polysilicon line and drawing it across a diffusion line. I must note that this process that is used for this design is a very simple process relative to that being used for integrated circuits in the 21st century. This has only about 6 functional layers, whereas the circuits today might have dozens of such layers and multiple levels of metal, whereas this only has 1 level of metal. So, but this process was used for creating a lot of the early integrated circuits, including microprocessors, and so is actually quite useful and quite functional the way it is. So I've created a transistor down here. I'm now going to go up here and create another one that is part of the design. And I need to make this one a little bit wider so I can select a point and then stretch it to this level like that, and so we have a bigger transistor. I'm going to then do some further design work in terms of connecting that transistor to other elements. So I'm going to need my need to put down a bigger layer here. I need to put down a contact. I need to put down a diffusion layer, and I need to put down another contact, and then those need to be connected together. And you can extend this out in that way. So this is the process by which you would go about creating things. Now, one of the tricks of an integrated circuit is that you want to make it as small as possible. And I see there's a lot of dead space here, so I may have to go back and optimize that. But let's proceed with a drawing a little further on, because we're going to make this into a shift register. And we're going to draw another polyline. So this actually creates another transistor that serves as a gate between this transistor, which is storing some information, and the follow-on transistor that's storing information. But before I go any further, I'm going to see if I can't make this a little bit smaller. So in order to do that, I'm going to select a certain area and say, take all of these items and I want to move them. So I'm going to click on this point and I want to move them up to this point. And now I have to shorten these lines, and so I have to select them and point at this and make it, if I do it right, I'll point here and go up there. Oh, I know. I'm using the move command as opposed to the. There we go. I have to use the stretch command as opposed to the move command, of course. So I take this point and move it up to here. And now it's quite a bit smaller in the vertical direction. I've got this up here. I got to select that and take this point and move it down here. So now, oops, it's after 40 years, it takes some practice to learn how to use the system again. And similarly, I could take this line here and move it over here, and that makes it a little more complex or simplified, and smaller. So now I'm going to take this, continue this diffusion layer that I had here, move it down so that it matches up with this one here, and then I'm going to draw over here, and I'm going to create another contact like I did here. So that takes a couple of contacts to one there, and then you have to put material around those contacts to make sure that they're really going to work. And so you get that. I don't want that one there. You can just hit the escape key to erase something if you put it in the wrong place. And then you have the contact. I'm going to extend this a little bit out here. And I have purposely sort of aligned this input with this output because I want to copy this circuit and not have to go through this process again. I want to be able to just sort of copy it and simplify my design by replication. So whether you were doing designs in the 1970s or in the present day, because of the difficulty in laying out individual transistors and so forth in a compact way, people are always looking for ways to simplify the design process, do one thing and then make copies of it. And so that's a very common productivity improvement in the world of integrated circuits. So you're always looking to design structures that can be copied in arrays or whatever that can simplify the process of doing the design itself. So I've created basically a bit of a shift register, and now I want to have a whole string of or a whole string of bits in this shift register. So I'm going to take this opportunity to design a symbol. A symbol is basically a collection of parts, individual items like what we've drawn, or it can be a collection of other symbols. And there is a specific menu command here for symbols, and I'm going to select that. And then you have a variety of different commands under the symbol menu. I'm going to define a new symbol up here called define symbol. So I select that, hit escape, and then you are asked to identify a reference point. So I'm going to identify the corner. I'm going to identify the upper left corner as my reference point for this symbol. And then I have to define the rectangle that surrounds the symbol. All symbols are rectangular. And I'm going to go out here and define this point here as that. And it then draws a line around the symbol and says, is that what you want? And you say yes. And then you can define what are called connection points, because later on it's going to make these items invisible, and all you're going to want to know is where can I connect to the symbol. So I'll say, well, I want to connect on the input, I want to connect on the control line here, I want to connect on the output, and I want to connect on the bottom of the control line there. So those are all my connection points, and I type escape, and I'm going to call this cell 1. So I've given it a name. It shows me what it's considering to be part of cell 1, and so I say yes, that's what I want, and I confirm it. Then it says, do you want to leave a copy of this, or do you want to just put it in the library? So I'm going to have it put it in the library, and so I do that, and now the symbol is gone. All these little pieces that were left behind are all left selected, and all I have to do is hit the escape key to confirm delete, and they all go away. So now what I've done is I've drawn a single cell, in this case the shift register cell. For other designs, you might want to design an arithmetic cell or a memory cell or a comparison cell. There's dozens of different types of cells that one might want to define that consist of maybe 1 or 2 transistors, 200s, or even sometimes thousands of transistors. And as I say, you can not only define the items within the cell or symbol, you can also combine symbols together and form a higher level symbol and use that in your design. So now I've saved that cell away, and I'm now going to, I want to draw the symbol. I want to draw it out into a shift register that's 12 bits long. So I want to select draw symbol. I hit escape. It says, what's the name of the symbol? I type the one that I just hopefully did. And it says, okay, where do you want to draw it? And I say, well, draw it right there on the screen. And how many do you want to draw? And I say, I'm going to draw 12 of them in the X direction and 1 in the Y direction. So I confirm that. And then I just do that, and it draws the outlines of the cells. Again, I know what's inside that cell. I don't need to see the details of it. And so it can draw it a lot faster and save memory by drawing it out this way. Now this is a good opportunity to show the advantage of working with 2 different windows. So I can click in the upper window. If I want to center the shift register, you can see there's 12 units or 12 bits of the shift register along here. Down here, I'm still looking at just 1 or part of 1, and you can see there's this rectangle which defines the portion of the upper window that you see in the lower one. If the upper window were to have the whole chip, for example, displayed, you could point in the upper window and say, well, I want to look at this last cell, but in detail in the lower window. So you can click in the upper window, and it will move the lower window to that position. If you want to see what's inside of that cell, you can make things visible. So you say, select the visible command. You can point at the symbol that you want to make visible, and it will then, you now see drawn out all of the details internally. And so again, I can go back to this upper, if I want to verify that they're all correct, or that things are connecting properly, I can go up to the upper window and say, well, show me the one in the middle, and it'll show that to me below, or show me the one, show me this left-hand edge, because I want to know where to connect down here. So I might, skip to that left-hand edge. I could then take this point, connect this connection point, and start drawing additional circuitry outside of this cell to connect it to the rest of the chip. So there are other commands available to you. If you want to go back to the main menu, one of the common ways of laying out a chip is to create mirror copies of things. So for example, there's a mirror command. It says, okay, I need to select an item first. So delete to abort, I select the item. I'm going to select this whole symbol, and I select mirror. And what do I want to use as the point of origin? So I'm going to mirror it around this metal layer down here, and I'm going to point at that point. Do I want to mirror on the X or Y axis? So I'm going to say I'm going to mirror on the X axis, and I don't want to move it. Copy or delete. So I want to make a copy, so I'm going to hit C, and it will now create a mirror copy of this same cell. I want to center this in the lower window so you can see more of it. You can make the window, the magnification in each window, you can change that. So if you want to see more in the lower window, you can do that and it will draw things out. You can again use the upper window to move around like this. And you can see how the symbol has been mirrored in that way. So this is a process by which you would create a complete chip in ICARUS. And as I said at the beginning, there are many, many different chips, dozens of different chips that were created using this product. When you got done with your design, you would then hit the output command and save the design to your disk in ICARUS standard format. We then had other software which would take that ICARUS file and turn it into a file that could be used in mask making. The standard back then and the standard today is GDS2. It's a format that was developed 40 or 50 years ago, and for reasons unknown to me, it's still the one being used. And so you would output it to that. You could then hand that file to any company that is capable of making masks. They take that, they make a different mask for each level of the integrated circuit. That mask then goes into the production line of the factory to define what the patterns are in each layer, and your integrated circuit comes out in that fashion. Normally you put one chip on one wafer and make thousands or millions of them. In our case, since we were designing, we had many people designing chips, and we were typically using them as test cases or examples. We didn't need large volumes, so we had another program that would allow us to array many different kind of chips on a single wafer. And so instead of one type of chip on a wafer, you'd have maybe 5 or 10 different chips on a wafer. And so when you made a wafer run, you got 5 or 10 chips out of it, as opposed to just one type of chip. And those would then be diced up, sawed into individual chips, placed in packages, and returned to the designer for them to test and validate their design. And that's the process that we used to sort of prove the overall process, prove the viability of ICARUS as a design tool, and prove the viability of teaching high-level designers how to implement their designs in an integrated circuit in a efficient manner.
I had 2 questions, Doug. One is about if you could talk about the sort of design rules that were with any particular kind of manufacturing process for integrated circuits, kind of what design rules were and how they're reflected in some of these, some of the numbers and the menus in the middle section between the two windows.
Okay. Yeah, I'd be happy to do that. One of the key elements of the what's called the Meade Conway design methodology was to worry less about the sort of final compactness of the integrated circuit and get the high-level design and high-level layout correct. And so whereas traditional semiconductor companies in the 1970s, 60s and 70s were optimizing their design rules at every possible case, it theoretically made for smaller chips, but also made the design process extremely complex because you had so many different design rules to follow. It was difficult to make sure that every one of them was met. And so part of the goal of the methodology was to simplify these graphical design rules. The design rules we're talking about are rules about how close 2 metal lines can be, or how big a contact between a metal and a polysilicon line could be, or how narrow a transistor could be. And so it's basically the width and spacing of each of these lines and how far they could be from each other. So we developed a set of design rules which we called that were scalable. That is, they were based on a scaling factor which we named lambda, and we defined all of the design rules in terms of lambda. So lambda was sort of half of the minimum dimension used in any given integrated circuit. So at this time in the mid-1970s, we were using a 6-micron design rule set. Today we are using design rules that are, I think, 1,000th of that, but back then it was 6 microns. So lambda was 3 microns, and a polysilicon line would be 2 lambda or 6 microns wide. A metal line would be a minimum of 3 micron or 3 lambda, or maybe 9, or often a little wider, 12 microns. Contacts would be 2 lambda or 6 microns, and you had to have at least 3 microns of metal or poly or metal, poly, or diffusion around those contacts to make sure that the contact was fully enclosed by the appropriate layer. So in each of these layers, for example, if I select the polysilicon layer here, it tells me that for this set of design rules that it's 6 microns wide, the flash or the square that goes around a contact is 12 microns on a side. And if I select, let's see, metal, for example, which is here, the minimum the line width here, default line width is 12, flash size is 12, and so you could change any of those numbers. You could draw the lines any width you want, but these were the most common widths that you wanted to draw the lines, and so you could sort of quickly sketch them, if you will, using the default line widths. So you could then, because the rules were not optimized for an individual process, you could say, well, I designed it with a lambda of 3, but now I have a more advanced process. Now the lambda is 2. So polysilicon lines are no longer 6 microns, now they're 4 microns, or 2 lambda, or 2 times 2. Metal lines are no longer 12 microns, but maybe 9 microns. So you could do that by optically shrinking, or in fact just processing the file at the output with a different lambda, and you could shrink the chips to take advantage of a more advanced process. So the design rules, although they were not optimized for any particular single process, allowed us to go to multiple factories and in fact shrink the designs over time without having to redraw it. Whereas if we had designed it optimized for a particular process, we may have had to redesign it to take it to a different process, or to do a shrink to take advantage of a more advanced process.
Two other follow-up questions, if I could. One was about the networking capabilities of the Alto. Was that in any particular way used in ICARUS, the fact of the networking?
The networking was really essential to all the uses of the Alto, I think. And in this case, you could use it to share design files or symbols. So people would often design symbols that other people would want to use, and so being able to put those on a file server, which you could then go and retrieve and reuse the symbols designed by somebody else, significantly simplified the design process. Of course, you needed to back up your design, so you'd want to use the network file server, and because of the modest resolution of the screen, you would also want to be able to make prints. We not only could print on sort of standard 8.5 by 11, but we had large plotters that would allow you to plot out very large layout plots, so you could make sure that all the pieces fit together. One of the challenges sometimes, you're working at a relatively low resolution on a very complex circuit, and sometimes you would click a couple of times, you may put down a piece of metal that you didn't realize that you'd done, and it was off in some other part of the circuit. And so you had to be careful of that, and sometimes you want to do sort of a final check of your layout to make sure that there were no sort of random pieces of material scattered about that you didn't realize were there.
In order to do that sort of print output, did ICARUS rely on any of these printing protocols that we've heard about from Xerox PARC, like press or interpress or things like that?
I forget exactly which format we use, but I think in general, yes, we just output to the standard format that was available. And I think in the case of the plotter, we probably had to do some special work because of the unique dimensions and so forth. But in general, yeah, we could capitalize on the printing capability. We certainly capitalized on the laser printing capability, and in fact, when we had color laser printers, we could print the outputs out on color printers. In fact, here's an example of a design, from the manual, if you will. These were laid out in color and could be laid out or could be printed on the color laser printer.
Last question I had was about if the limitations of the Alto in terms of either memory or the storage capacity of the removable disks, was that a constraint on the size of integrated circuit that could be designed in ICARUS, or was there a way around that, or would that have been just nobody was designing a circuit that big?
The biggest limitation was the RAM memory, the internal memory of the machine. In order to be able to move around and refresh your drawing and that sort of thing, you really wanted to keep your circuit in memory. And in order to do that, you wanted to make heavy use of symbols and not have a lot of sort of random pieces of layout laying around, because each of those used up quote-unquote item space, and there was a limited amount of that based on the fact that we only had 128 kbytes of memory, or 512 in the later Alto 2. And so that was definitely a limitation, and one that you had to be careful of. But you could still design reasonably complex chips as long as you were careful about building hierarchy. So you design things in a symbol and then put those symbols together and put that in a symbol. And so as long as you could kind of keep building up a hierarchy, theoretically there was no limit to how big you could do it as long as you could build that hierarchy. And that also fit very well with the design methodology that we were trying to promote. So the limitations of the computer provided some discipline to make sure that people followed a more regular design methodology. One of the fundamental method, the fundamental strategy for attacking complexity was regularity, of doing things in a regular fashion. Because if everything's done randomly, you just have the complexity grows literally exponentially, and you just can't keep track of things. You can't check it, you can't verify it, and so forth. So the limitations of the Alto helped, by the way, to enforce this hierarchical design methodology, which was a better way to do things. Much like it's the same practice that's followed in programming. As you write subroutines and that sort of thing, people don't just write linear code that's hundreds of pages long. They write a whole bunch of subroutines. Those subroutines get reused, linked together in different ways. You have defined interface points. Exactly the same thing happens in a well-structured integrated circuit.
Before I ask you to show us one last thing, let me just check and see if anybody else has any questions or something.
Yeah, sure.
Yeah.
I was wondering if you could talk about how ICARUS influenced later VLSI design tools, including ones made by companies that you were involved with.
After we had finished the work on ICARUS in 1979, late 79, I decided to leave Xerox PARC and join a startup called VLSI Technology. The VLSI Technology was founded on many of the same principles that we've talked about in terms of design. And so because at the time design tools were not commercially available that would support the methodology that we wanted to promote, the first major investments that we made at VLSI Technology was in the development of a design automation group, which was virtually unknown at the time for a semiconductor company to have its own internal design automation group. And so when I left, not surprisingly, I asked Jim Rowson, who had helped develop ICARUS, to join VLSI as the head of our design automation group. And he put together a team that used many of the same ideas. We didn't have Altos available, but we bought, by this time the industry was starting to catch on to the idea of a workstation, and Apollo was the earliest vendor in that category. So our first workstations were Apollos, and we developed tools that very much sort of took from the ICARUS idea, but expanded significantly on that in terms of all the other tools that we developed. And I think, I think it was 1979, Jim and I gave a paper at the Design Automation Conference, perhaps it was earlier, and it was really, this was the first integrated circuit design program available on a workstation. So workstations were a brand new concept. Most people weren't even aware of them. And so I think that demonstrating this capability and the fact that you could do interactive design on a relatively low-cost workstation sort of paved the way and instigated changes across the board. And in fact, in that same time frame, in 1980-81, three of the earliest and most important influential design automation companies were formed: Valid Design Systems, Daisy, and Mentor Graphics, and all of them started to or were formed around the idea of doing interactive design both at the board level and at the integrated circuit level using workstations. And I think that the demonstration of ICARUS on the Alto, the combination of an independent workstation and integrated circuit layout served as an impetus, and they were the companies that really launched the design automation industry as we know it today. So yes, I think that ICARUS and the Alto had tremendous impact, just as it did in the personal computer field, it did in the workstation field.
Last request, could you show us, Doug, how you would save this design that you've made, and then how you would exit from ICARUS? Okay,
so there is a command here, save drawing. If this were my complete design, or if I just wanted to save it and go off and do something else for the moment, I can save the output on a file called shift register bit.ic. IC is the extension used for ICARUS files, and then you just confirm that, and that file already exists from a previous work, so I'm going to overwrite that, and it writes it on the disks, and then it's available for, I can either come back to it later, I can then quit the design and confirm. And the beauty of the Alto is that now I can go do my word processing. I can do design at board level design using the SIL design package, and I can use the graphics packages all at the workstation, just like we're used to today.
Well, thank you very much.
Actually, I have one more question. You kind of touched on it, but what is the direct ascendance from this program to the way chips are done now?
Well, I think I think it's partially this program, and perhaps more importantly, the methodology and book that was written around this. This program allowed us to sort of prove out the methodology, but the tremendous impact was the methodology originally conceived by Carver Mead that was encapsulated in the book Introduction to VLSI Systems, written by himself and Lynn Conway. And that book, along with some videotapes of courses that we taught at VLSI Technology, were then spread literally to hundreds of universities around the world. And people started teaching VLSI design courses in dozens and dozens of different places. And those people then became the fuel, if you will, for the changes that took place in the 1980s. The existing companies using existing design methodologies, as is so often the case, were slow to change. But the new companies that came along, so for example, in design automation area, the dominant companies at the time we were doing this were Calma and Applicon. They depended on very large workstations costing hundreds of thousands of dollars, operators to digitize drawings that were done by hand, literally by hand with color pencils on Mylar. And so this was a tedious, difficult process, very sort of skill intensive at a very low level, but not at a design level, but at a graphical level. And that was the process used by Intel and every other semiconductor company in this same time frame. With the advent of the workstation, with the advent of products or capability like ICARUS, and a whole new rush of students coming out of the universities, many different startups formed. There were dozens of different design automation companies formed. There were dozens of different semiconductor companies formed. And there was really a complete revolution, if you will, in terms of who's doing design, how is the design being done. I mean, the example that I gave of silicon graphics, Jim Clark was an architect. He was a computer architect. He didn't do level design, but he used ICARUS to design a complete chip which worked and could demonstrate the fundamental characteristics that were enough to give himself and others the confidence that they could go off and form a company, Silicon Graphics. They then used tools to design custom chips and developed a whole, very large company based on that. That's just one example of how this idea of architects being able to reach all the way down to the integrated circuit level and not do it in the traditional way, but do it in a very regular kind of methodical way, and come up with designs that people would never come up with if it was using the same standard process. And so it was the combination of the workstations, of these tools, and the design methodology which caused a major shift in the semiconductor industry through the introduction of dozens and dozens of startups in each of these different areas.
Maybe I have, I guess, a final request, Doug. It would be interesting if you could show us how you would launch the program from this basic prompt, and if you could bring back the circuit design that you just created.
So you type ICARUS. It says how much library space do you want? This is an indication of how much memory you want to use and so forth. Okay, I'm going to have to remember. I don't. I forget the name of the
Me too.
file that I just typed. Probably don't want to record this.
Well, no, this would be how somebody would actually have used it if they forgot what they called their design.
So there's a directory.
I think if you hit tab, oh, there it is. Shift-reg.
Oh, shift-reg-bit.ic. Shift-reg-bit.ic, okay. Okay, you go to Get Drawing, hit Escape. shift reg bit dot IC. There it is. It came up. It shows you that it's off the display over here. So I would center it in the lower window, and then I could make it visible. To go to my symbols and make this visible. And I would retrieve it that way.
Thank you very much.
I do have one more question.
Go ahead.
What are the major software tools in this space today, and the major companies that make them, and how did they get to be the major players?
Okay. The major companies today are Synopsys, Cadence Design Systems, and Mentor Graphics, I think in that order. All of them have grown both organically and perhaps most importantly through acquisition. Each of them has acquired dozens of different companies. As is the case in so many other industries, as we see here in Silicon Valley, when something new comes along, there are literally dozens of companies that start up and are doing little niches or pieces of that. And then you start to consolidate those companies over time. Cadence was actually formed out of two major companies. One was Solomon Design Automation, and another company called SDA, I think, not SDA. I forget the name of it, but there were two companies that were formed to form Cadence, and then Cadence has gobbled up literally dozens and dozens of other companies, including one that I started after I left VLSI Technology. I formed Redwood Design Automation, one of these small startups, and we formed it in 1990. It was not focused on design, but on verification of integrated circuits. Cadence purchased that company in 1994, combined it internally with another company which they'd bought the year before, and we formed a sort of an internal group within Cadence. But Cadence grew by so many acquisitions. Synopsys for a long time grew very organically, but then over time they also became major acquisitors, if you will, as did Mentor Graphics, such that there's continued to be new companies started, new companies bought, but for the last 10, 15 years, Cadence, Synopsys, and Mentor have been the major players. Mentor, of course, was a couple of years ago bought by Siemens, and so they are no longer independent. So in terms of independent companies, Cadence and Synopsys are the major two players today. But it followed, the design automation business followed very much the pattern of so many other startups, whether you go back to the automotive industry or the computer industry, the design automation industry. Lots of different companies, which ones are going to grow, the biggest ones start gobbling up the other ones, and you wind up with 2 or 3 major players.
Well, great.
Thank you.
Thanks. Thanks a lot, Doug.
All right, my pleasure.